Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to talk about derivative formulas. In the previous video we talked about using the limit definition to find derivatives, which I'm sure you will agree is a very long process, very tedious, and can get very complicated depending on the function. So now, instead of using the limit definition, we're going to look at the existing formulas for finding the derivative. Before I start those formulas, I just want to talk about notation. We did discuss in the last video one notation, which was dy dx. I really like this as notation, especially when we get into other variables other than y and x, and particularly if you have a function where there's more than one independent variable. This tells us what we're differentiating with respect to. So I quite like this. Y prime is also acceptable for derivatives. F prime of x is also notation to indicate derivatives. And d of the actual function, dx. So here you would actually put the function in, whether it's an algebraic function, a trig function, or whatever. And that's saying the derivative of this actual function d with respect to the x variable. So you can use any of these for derivative notation. Let's now take a look at some of the formulas. Our first formula is if our function is equal to a constant. So y equals c, where c equals a constant. So that constant could be 5, could be -1. It's a constant value, and if we were to graph it, it would be a horizontal line. So let's say this is y equals 2. The idea of a function being constant tells us right away that the rate of change of that would be 0. Constant means it doesn't change. And remember, derivative means instantaneous rate of change of a function. So if you take a look at this function, y equals 2, it never changes. It stays 2 for all values of x. So the derivative of a constant is 0. Our second rule deals with a power function if we had x to some power n. And the derivative of that kind of function is defined as n times x to the n minus 1. That's going to be true if n is a positive integer, negative integer, fraction. Doesn't matter what the exponent is, it could be a 0 exponent. This rule would apply. So let's take a look at some examples of using this rule. So our first example, we have y equals x squared. So the derivative will be n, which in this case is 2, times x to the n minus 1, 2 minus 1 will be 1, which we would just write as 2x. That's the derivative of that function. In our next example, if we have x to the 5th, the derivative of that function would be 5, because n in this case is 5, times x to the n minus 1. 5 minus 1 is 4. That's the derivative. Our third example has a negative exponent, but our rule is still the same. We take n, which is -2, times x to the n minus 1. -2 minus 1 will be -3. Typically, when we're working with negative exponents, we don't keep negative exponents, but when we're finding derivatives and you end up with a result with negative exponents, it's probably acceptable to leave it that way. So you could write this, you could leave it like this, or you could write it as -2 over x to the power 3. You'll need to find out what's expected by your teacher. Let's take a look at a few more examples. So my next example is 1 over x cubed. We can't differentiate it in that form unless we were to use the quotient rule, which I haven't talked about yet. I don't know how to differentiate 1 over x cubed. I only know how to differentiate a function that's x to the n. So we need to write this whole function as x to the n. I don't have a rule for 1 over x to the n right now. So I'm going to rewrite this or rethink this as x to the negative 3. Now that I've got it in the form x to the n, now I can differentiate it. I can find the derivative, and it will be negative 3, my n value, times x to the n minus 1. Negative 3 minus 1 is negative 4. My next example, y equals square root of x. I can't differentiate that in its present form. I need to think of it as x to the n, and the definition of square root means x to the power of 1/2. Now I can differentiate it because I have it of the form x to the n, so my derivative will be 1/2. X to the 1/2 minus 1 would be negative 1/2. Can be left in that form, or I could write that as 1 over, put the 2 in the denominator, put the x in the denominator, and then my exponent becomes positive. I can also express that as 1 over 2 root x. So all of these three answers are equivalent. It's going to depend on what you're expected in terms of a final answer. Now the next question, you might see, again, we can't differentiate it in the form that it is, x times root x. All I know right now is x to the n. But I know that when I'm multiplying, this is like x times x to the 1/2. And my rules of exponents say that that's equal to x to the 1 plus 1/2, which is x to the 3/2. And if you're rusty on your rules of exponents, I do have a video that you can go and take a look and review those rules. Now that we have it x to the n, we can differentiate it. We can find the derivative. It will be n, which is 3/2, x to the 3/2 minus 1. So 3/2 minus 1 is 1/2. So that would be the derivative. So some of these functions you might have to do a little bit of manipulation on the function before you can differentiate. Okay, let's take a look at another rule. Our next rule deals with a constant times a function. And what I'm going to do is call that function u. So far, the only function of x that we've looked at is x to the n, but we are going to get into other functions as we progress. So this rule applies for any type of function of x. So the rule says that if we have a constant times a function of x, I want to just make a point of saying that a constant times a function is very different than a constant by itself. A lot of students will see a constant and think the derivative is 0, only if the function itself is a constant value. That derivative is 0. But if you have a coefficient times a function, then this is the rule we're going to apply. The derivative of a constant or coefficient times a function will simply be the constant or the coefficient times the derivative of the function. I think it's best to show examples to help you understand this. So in our first example, we have y equals 2x cubed. So the derivative of this will be 2 times the derivative of x cubed. The derivative of x cubed is 3n times x to the n minus 1. So 3 minus 1 is 2. We can clean that up a little bit, and our derivative will be 6x squared. So that's all that rule means. You just keep your constant there and then find the derivative of the function. In this example, we have 4 over x squared. I don't want to have 4 divided by x squared. I want 4 times my function of x, or my x to the n. So I'm going to rewrite this as 4 times x to the power of negative 2. So when I take it out of the denominator, the exponent becomes negative. Now I can apply my rule. The derivative will be 4 times the derivative of x to the negative 2 will be negative 2, that's my n, times x to the negative 2 minus 1, negative 3. We can clean that up. 4 times negative 2 is negative 8. And then I can put this in the denominator if I want to express it with positive exponent. So again, you have to sometimes do a little bit of manipulation of the function. You can't simply just go in there and take the derivative of that and take the derivative of that. It will not work. Our next example has to be rethought before we take the derivative. I don't know how to take the derivative of a function divided by a constant. But what I do know is that I could rewrite this as 1/5 times x cubed. Once it's in that form, now I can differentiate it. So the derivative will be 1/5. The derivative of x cubed will be 3 times x squared. So that derivative can be simplified to be 3/5 x squared. Now if you wanted to write it as 3x squared over 5, that's fine. I generally like to keep my coefficient, my constant part, separate from my function. That way if I need to do anything else with derivatives, it's in a form that I can use, but both are correct. Let's take a look at one last rule. I want to introduce one other function of x I'm going to call v. I'm not crazy about the letters u and v, but it's pretty standard in a lot of math texts just because u and v look very similar, and if people write them in a sloppy manner, then it's easy to confuse the two. But I'm just want to be consistent with what math texts generally use. So u is a function of x, v is a function of x. And you may find that you have a function that has more than one term. So you have some x to the n function, you have another x to the n function, or constant. It could be anything. It's very simple to find that derivative. You just take the derivative of each term. So the derivative will be u prime plus v prime. We use the word prime to indicate the derivative, so y prime is the terminology that's used. So the derivative of y in this case would be the derivative of u plus the derivative of v with respect to x. I could do another rule where I had y equals u minus v and then take the derivative. So the derivative of y would be the derivative of u minus the derivative of v. Or I could just combine the two rules together and say that if it's either addition or subtraction, you simply take the derivative of each term. So again, let's take a look at some examples where we can use this rule as well as the other rules that we've talked about. So here we have a polynomial function. We have more than one term. To find the derivative, I just take the derivative of each term. In order to find the derivative of this first term, I leave my constant and then I multiply by the derivative of x to the fourth, which would be 4 times x to the 4 minus 1, so times 4x cubed. In this next term, remember that that exponent is a 1. When I take the derivative of x to the 1, my n is 1, so it's 1 times x to the 1 minus 1, which I'll simplify in a minute. My last term is a constant. We learned our first rule says that if we have a constant, the derivative of a constant is 0. So now it's just a matter of cleaning this up and making it look nice. So we've got 12 times x cubed plus 2 times x to the 0 is 1. So 2 times 1 is just 2. So this is the derivative of this function. Last example. The derivative of this function will be the constant times the derivative of x to the 6th, which will be 6 times x to the 6 minus 1, plus 3 times the derivative of x to the 4, which would be 4x to the 4 minus 1, plus we have a constant. The derivative of a constant is 0. Now, if you can go right from here to this step, that's not a problem. I just want to show every step along the way so I don't lose anybody. So this would be the derivative of this. So practice examples that are similar to this as much as you can, and then when you're ready, we're going to move on to more examples, but a little bit more different.